Okay, we are now going to speak about interferences in atomic spectroscopy. Uh, there are different interferences that potentially can happen in an atomic spectroscopy method. We have two types of interferences. One of them is a spectral or blank interference that is due to a spectral overlapping, and the second one is analyte interference that is divided to physical or non-specific and chemical or specific. In this interference, we have alteration of AA signals due to chemical or physical processes. But what is the sources of spectral interference? We may have two different sources in atomic absorption or atomic emission lines. Sometimes we have interference. What does it mean? You see, each element, as we discussed it before, each element has several emission or absorption lines. These lines are usually very narrow, but in some cases, maybe these lines have exactly or almost the same wavelengths as the line of another element. So if you have several elements in a solution and then introduce the solution into a flame, for example, so you will have the emission or absorption lines of several elements that some of these lines may interfere. So this is called line interference. Another type of spectral interference is background interference, that is coming either from scattering of the source beam by small particles, solid particles. There may be solid particles in the atomizer, for example, carbon particles, that they can scatter the beam of the light. And also we may have some molecules that have molecular bonds instead of lines. So broadband absorption by molecular combustion products is another type of background interference, that this one is much more important. But about the physical or non-specific interferences, we should say that this type of interference can change in the when a change in physical properties such as viscosity, surface tension, flow rate, etc. happens, this can make interference. So if for any reason, the viscosity of the sample change or the flow rate of the sample change, this will make errors, make problems. So this is a type of interference that is called physical interference. But another type of interference is chemical interference. That is two types. One type is formation of low velocity compounds. For example, when you are going to measure calcium, if you add some phosphate to the solution, phosphate can interfere with calcium because calcium phosphate has low volatility, and it therefore the sensitivity of measuring calcium will decrease. So this is called chemical interference due to formation of low volatility compounds. But how can we overcome this problem? There are two methods. One method is using a releasing agent. For example, if you add some strontium to a calcium phosphate solution, strontium can Strontium can make a, compound, a molecule with phosphate. And the tendency of phosphate to strontium is more than calcium. So when you add strontium, the phosphate will go around strontium, and calcium will be released. So this is called releasing agent. Another method is using a protective agent. In this method, we add a complexing agent like EDTA that make complex with calcium and will free it or protect it. It will protect it from phosphate. So this is called protecting agent. So these are two common methods for overcoming this interference. Another interference is ionization equilibrium. Uh, some of the elements may be ionized in an atomizer. For example, in flame, if you are going to measure strontium, some of the strontium will be ionized. Uh, for example, 90%, 80% of its atom, but 20%, 10 to 20% of it may be ionized. So, and this is not good because it will decrease the sensitivity of strontium. And as you know, the wavelengths of an element is different from the wavelengths of its ion. So when you are measuring an element, if it's converted to ion, the sensitivity will decrease. So one way to overcome this problem is to add some electron to the flame. For example, if you add a high concentration of potassium into the solution and introduce into the flame, potassium will be easily ionized and make a high concentration of electron. So according to Le Chatelier principle, when you have a high amount of electron, the equilibrium will return back to its left side. So because strontium is in equilibrium with strontium, with its ion, with strontium ion and electron. So when you add electron, the equilibrium will go to the left side, and less ionization will happen for this metal, and then the result will be higher sensitivity. In the next picture, you can see this effect when you this is the strontium signal as the concentration as a function, this absorbance of strontium as a function of strontium concentration. And as you can see in this picture, when potassium concentration will increase, then the slope of this graph is increased. It means that the sensitivity of measuring strontium has been increased by increasing the potassium in the sample. That is for the reason that I explained. Okay, then we are going to talk about radiation source. You see, as I said, we have to use a radiation source in the atomic absorption instruments. Also in the atomic fluorescence instrument, we have a lamp or radiation source or light source. The light source that is used in atomic spectroscopy is a line source, not continuous. It is not it doesn't have continuous emission. It has line emission, that is more appropriate for atomic spectroscopy. One of the most important and most common radiation sources that are used in atomic spectroscopy is hollow cathode lamp, that its picture can be seen here. We have a hollow cathode that is made from the element that we are going to analyze it. For example, if you are going to analyze copper, the cathode should be made from copper. If you are going to analyze nickel, then the cathode should be made from nickel. And then we have an anode that is made from tungsten or something like that. Inside the lamp, we have a low pressure of an inert gas like neon or argon. So when you apply a high potential between anode and cathode, the inert gas inside the lamp will be ionized, and then the ions will bombard the cathode surface, and the cathode element will be evaporated into the gas phase. This phenomena is called sputtering. So by sputtering of the metal atoms into the vapor phase, some of these atoms are excited and emit the light. So the lamp will be turned on in this method. So in this way, so we will have a light that has exactly the emission lines of that special element. So for each element, we should have its own lamp. So if you want to analyze 5 elements, then you cannot analyze them just by using one lamp. So for each element, you should change the lamp in the instrument. So first, for example, you can use the copper lamp and measure copper, and then use the nickel lamp and measure nickel, etc. Here you can see some of the hollow cathode lamps, the picture of some hollow cathode lamps. The lamps in the left side are new lamps, and the lamps in the right side are old lamps. That you can see that the surface of the glass has been mirrored. Some vapor of the element has been deposited on the surface of the lamp, and this is an old lamp that usually should be changed. So if you use a lamp for several years, then you have to change it. It is not forever. This is another picture from inside of the lamp, and you can see clearly the hollow cathode inside in the middle of the lamp. Another type of lamps are electrodeless discharge lamp, which is called EDL. In the EDL lamp, you don't have any electrode, so it is electrodeless. It is without any electrode. In this lamp, you have a few micrograms of the powder of an element that is in this bulb or lamp, and then we have an inert gas again in the lamp. Here also we have an inert gas like argon or neon, and a few milligrams of the powder of the lamp. But then we put this lamp in an RF coil, and then we use a generator or RF that can light this lamp by ionization of the inert gas. So in this method also the gas will be ionized and then can bombard the atoms, the powder of the element that and then we will have emission of that element. But instead of RF coil and instead of radio frequency coil, we can have microwave coil also, and we can have microwave energy to light this lamp. So we have two different type of EDL lamps. One of them is RF lamp, RF EDL, and the other type is MW EDL, that's microwave EDL. Both can be used. This type of lamps have 10 to 100 times more intensive than the EDL, than the HCl lamp, but they are more expensive also. These type of lamps are not very common because they are expensive, and the hollow cathode lamps are more common. This is the picture, another picture of the EDL lamp. Okay, here we are going to talk a little about monochromator. You see, we have two type of monochromator to separate the different wavelengths, the light, to separate different wavelengths of the light. In the upper picture, you can see that the prism, a prism that is used for separating the or dispersing the light into its components. And in the lower part you can see a diffraction grating. In old days usually prism was more common, but today grating is more common than prism, because grating is much more efficient than a prism. But what is grating and how does it work? Here you can see different parts of the monochromator. The upper figure shows the prism and the lower one shows the grating. A monochromator has 5 different components. The first one is entrance slit. The second one is collimating lens or mirror. The third one is the dispersion element, that is prism or grating. Then we will have a focusing lens or mirror, and then finally we will have an exit slit. So 5 components of a monochromator. When we want to change a wavelength, it's just enough to turn the prism or turn the grating. By turning the grating or mirror, grating or prism, we can focus different wavelengths on the exit slit of the instrument. Here you can see the structure of an Ecklet type grating. That is an important type of grating. In the left side you can see that the reason that grating can disperse or diffract different wavelengths is the constructive and destructive interferences of different wavelengths. By turning grating or by changing the incident light, incident angle or reflecting angle of the grating, different wavelengths will be passed over the grating. So you can by turning the grating, and by changing the incident or reflecting angle, you can focus different wavelengths on the exit slit, and this is the method that is used in atomic spectroscopy uh, uh, scan different wavelengths, or to select a special wavelength for the instrument. Here you can see different parts of an atomic spectroscopy instrument. This is the double beam design of atomic absorption spectroscopy. In the left side, again, you see the lamp. Then we have a part that is called chopper. A chopper is used to modulate the light of the lamp and change it from DC to AC. This is necessary uh, mm, to remove the emission of the to distinguish between the emission of the flame and emission of the lamp, because the detector cannot distinguish between these two unless we make the light of the lamp we make the light of the lamp an AC light, and by using the chopper will turn, and in this way we will have uh, an AC light of the lamp that can be distinguished by the detector from the continuous light of the flame. I think this one was the last slide, yes, of this part.